Alright, hell yeah, we got dynamics and we're doing derivatives. Now this is part 5. So we've already in part 4 taken the derivative with respect to the angle, and we are able to get the velocity. So what we're going to do is, you know, one thing when working with derivatives, I was like, can you mess up? You know what I mean? So I guess what I'm going to do is we are going to, well actually we're just going to use this. Let's see if we can just use this photo. So things that are constant, this eccentricity, this radius, and so what we're going to do is just anywhere where we can do the radius, you know, draw that in. So to that, this is the follower. At A it goes up and down as this disc spins around kind of lopsided. Alright, booyah. And then I'm just going to draw a line there and then a line up here. So even though this triangle is small, I think we're pretty good. Part 4, we do a bigger blow up of this. And in part 1 and 2, we actually use this model to show you, you know, at 0 degrees, the actuator is up here. The actuator comes down. At 60 degrees, we're right here. So, you know what I mean? That actually doesn't come down a whole lot. But then from 60 all the way to 0, hell yeah, we come down quite a bit. And then pop all the way back up. Anyway, alright, so, but this video is going to be about, hey, can you mess up the differential process? Or can you make it harder on yourself? Is there a way to make it simpler? In part 4, we try to do the simplest approach. We're going to say that this is theta. I'm going to say that this angle is phi. Sorry, this is so small. But I think we're good. So we have a hypotenuse here. We have a right triangle there, right triangle there. So this hypotenuse is E. This hypotenuse is the radius R. And so typically what we would say is, well, let's definitely blow this up. So booyah, we got this. And we have this is E. This is R. This is theta. This is phi. So we can start kind of labeling these. If the sun is shining, this has to be the signing. So we have the E sine theta. This is the E cosine theta component. So if we make sun shining rays, this is going to be the sine component of the angle. So we're going to have R sine phi. And what the sine means is the percentage of the hypotenuse. So here's my right triangle. Here's my hypotenuse. The hypotenuse is always the larger number. If this is a 30-degree triangle, hell yeah, remember that one. 50% of this number is going to be this direction. And then the other way to look at that is just like, hey, always divvy up the hypotenuse. At least divide it in 2 and be like, oh, okay, yeah, this length actually looks pretty close to that. Actually, this is less than a 30. You can see that this length is less than half. So then you know this angle is less than 30. Okay, booyah. All right, so to do this problem, we need to find the velocity of A, and we need to start out by finding the position of A. So this is the origin of rotation, and then this is A. So at this angle, just whatever angle, you know what I mean, we're just kind of choosing an angle. The angle could be at 0, but when we play it out, we get these two triangles to form. And so, and then we have a relationship between them. Kind of the general gist is that if I know theta, I know what this angle phi is. You know, and we're gonna show this the case. So we have R. If this was the sine R sine phi, this is going to be R cosine phi. Sorry, I didn't write that in. Okay, so we have even right here, like, hey, that distance. And we're going to say that this whole distance right here is going to be y. So we have, we're going to call that y. You know, we could even call this x. And so, cool. And so, but we want to get theta in terms of, well, I don't know. I mean, right here we could just say, hey, we already know y. Y is going to be r cosine phi plus e cosine theta. And the general gist is like, hey, let's take the differential of this equation. We can change y with respect to time, and then we'll get something. We'll get the velocity. This is the velocity. This is the velocity of A. It's the change in this length with respect to time. So that's kind of where the differential aspect occurs. But one, we can't differentiate with respect to, well, we could. We could just differentiate this. We're going to have to use the chain rule of differentiation anyway. So let's actually do this, because it might be kind of a simpler way to go. Just to show you, you really can't mess up. So we're going to differentiate. So how you would write this is you would say d r cosine phi plus e cosine theta dt. But I don't have a t right here. I don't have a t right here. But you could also write this. Hey, this is also differentiation of this with respect to time plus the differentiation of. So let's write that in. Just kind of small. Just to kind of show you the properties of differentiation. Because you could see that, hey, if I change this and then, divide it by the change in time, and even that is just like, well, what the hell does that even mean? You can, basically, let's say this thing is going to be at angle 0. And then I just say, hey, 1 second later. I kind of made up my own problem in phase 1 and 2. I just kind of, in part 2, I was just saying, hey, let's just make these 1 second so we can get kind of a visual representation of what's going on here. So if we do this, if we say, hey, that's going to be 1 second until this gets to here, we could actually see what this angle sweep was. It's 45 degrees. So in that problem, like, hey, every 45 degrees was 1 second, and then we go to 45 again, and then we're right there. So, that's an interesting way to have a change in time. And so, if we wanted to, if in this problem we could have just said, 45. I don't know. Let's say we wanted to find the velocity of this slider at 1 second. Well, basically, we would find the velocity at 45. 45 plus 90 is 2 seconds divided by, 60 divided by 90 times 2. So our problem basically is just at 1.33 seconds, that's going to be 60 degrees. So I want to know the velocity of this slider at 1.33 seconds. The other aspect of that is, hey, if at 1.33 seconds is 60 degrees, I want to know at time of 1.3 what is this theta, and then what is this phi. You know what I mean? And I know what theta will be because we have d theta dt is omega, is the radians per second. It's theta dot. And I've already solved for it. It's going to be like 104 radians per second. Use factor label. You take 1,000 revolutions per minute. You take 1 minute divided by 60 seconds. That's going to be revolutions per second. So that's this part of the radians per second. We need to say 1 revolution is 2 pi radians. And hell yeah, you'll pop out that number. Okay, so let's go back to the differentiation. And so, hell yeah. So you could change the time, and then that time is going to have... Alright, but I better catch myself, because this the process of actually taking a differentiating this with respect to whatever gives you equation of the velocity at those angles. So if we get that equation, we just need to figure out what the hell was I even doing? Was I saying, like, what does this even mean? Like changing this value and then changing time. Yeah, I can talk about that because we did that in part 3 and part 1. Is that you have to, at the angle 60, in whatever angle this would be, you have to, you know, that's, you're going to take your, you're going to find your, yeah, you're going to find the position at that time, change the angle just a little bit, and know that change in angle is associated with the change in time. Find that new height, and so the change in that height, and then divided by the time it took to make that change, is your velocity. Man, so I do a pretty good job of explaining the chain rule in part 4, but I don't know. You know what I mean? I think I'll get better. I'm not going to use the words for it, but hell yeah, we don't have time right here. And we don't have oh, is that where I went? Is like, hey, we don't have theta as a, not really, but you can make theta as a function of time. Right off the bat, at time 0, maybe this thing is vertical. So you would have theta is equal to 0, and then you have an angular speed. So that equation would just be like, hey, theta is a function of time is theta naught, maybe that's 0, plus omega t. And if theta is 0, theta is a function of time is just omega t. When we... at theta 0, phi is 0. So phi as a phi as a function of, let me write this again. Phi as a function of time is also phi naught plus, but now this isn't omega. You know, omega is, I would say it's theta dot. So theta as a function of time is going to be theta initial plus theta dot. Phi as a function of time is going to be phi initial, but it's going to have to be its own angular speed. So the angular speed of this line right here is going to go process with the circle. But the angular speed that this opens, that this angle like opens up and gets smaller, will... because that's gonna, let's kind of take a look at what angle that is. So here's the vertical. Oh, I'm losing it. All right, hell yeah. So we're back, and yeah. So let's get this in here. So if this is in the vertical position, and then we play it out. Here's the center of the circle, and so this angle is the one that's changing. And so heck yeah, so it's something, it's still something, it's 0 at 180, and 0 and 180, that angle is 0. So if we come out just a little bit, we're going to get a little bit of angle. And down here we're going to get a little bit of angle. The most that angle could be is only about 30 degrees. So this angle varies from like 0 to 30 back to 0. But this theta progresses from 0 all the way to 360. And just keeps going, you know what I mean, as the circle goes around. But this angle kind of goes out and back. And so just kind of keep that in mind. Alright, so because of that, theta dot, this has to be, you know, this is not constant. It goes one way and then the other, and so it has to be a function of something. So theta dot will be, you know, some function of, you know, just all those parameters. So hell yeah, keep that in mind. Because if we do just differentiate this, we do the chain rule, and we say, I don't have a t here. You know, I could put the t's in, but even that, I don't know what this is as a function of t. You know, I would have to do my own separate, you know, equation for that. Okay, so let's continue on and maybe see where we run into that issue. So I don't have t right here, I don't have t right here, so I can't differentiate with respect to time, but I can differentiate this one with respect to phi, and I can differentiate this one with respect to theta. So that's the chain rule. So I do d r cosine phi. Now if it helps, put the top in parentheses. You are changing this little bit. You're changing this function, and then we're going to do d phi. I can do that, but then I got to go d phi dt, and just know that this is going to be that phi dot. Okay, hell yeah. And then we're going to add it to d theta, so we're going to differentiate e cosine theta. If you put it in parentheses, this is the function you're changing. And with a change in angle, with like a 1 degree change in angle, you know, how much is this changing? Now, it's kind of like, who cares? But then when you couple that with d theta dt, these d thetas cancel, and you get this. This is a portion of this y direction. See how this is y? So now you get y, you know, how much y changes as a function of time. That's velocity. That's the velocity of this little chunk changing. But we need the velocity of a, which is the changing of this chunk plus the changing of that chunk. Hell yeah, that's why we're doing them both. And this is going to be theta dot. Let's differentiate this. We have a constant, so it's just going to be r. Now cosine. Cosine goes like this. It's going to be, at 0, we get a 0 slope, so that's going to be sine. Sine of 0 is 0. So hell yeah. So derivative of cosine is sine, but this slope is negative. You can see that it's always negative. So we got negative 1 sine phi. I just like to throw the 1 in kind of like a product bracket. And cool, so we differentiated this, and now we have this phi dot that we have to multiply. That's part of that chain rule. Let's go to the next one. We're going to have e as a constant. We have cosine again, so it's negative 1 sine phi, and then phi dot. This is the velocity at a. Like, cool. Like, are we done? I mean, anytime you do using the rules of differentiation, always check units. So sine is a percentage. So that's a dimensionless. So I'm just going to put dim right there. This is angle per second. That's in radians per second. So radians per second is dimensionless per second. You know what I mean? So we do have 1 divided by seconds right here. And then r is in meters, let's say. It's in millimeters, but just meters per second. Sweet, so that's going to be velocity. Here, meters, dimensionless per second. Cool, that's going to be meters per second. So we have a check on units. All right, so, but now, what do we know? That's the other thing, is like, when you set up even the geometry, you're like, do I know the angle? Well, sure, I'm going to, at 60 degrees, I want to know what's going on. So I know that angle, I know the angular speed, so I know theta dot once this pops up. So I know theta dot, I know the angle at 60, I know the radius, I know the eccentricity. I really don't know. I've not put anything together to actually figure out what phi is. If theta is 60, I don't know what phi is. You know, and then the other thing is, like, I don't know what theta dot is. So we're kind of at a roadblock right here. So let's go back to our geometry and see that, hey, this, like, these two parts of the triangle share a common side. So we can say that this side in relation to theta is equal to that side, r sine. So we're going to say that e sine theta is equal to r sine phi. And now we're going to solve for phi. I'm going to get phi over here. Well, I shouldn't do this but I guess I'm going to do this. I'm going to bring the r downstairs over there, get rid of it. And then I'm going to take the inverse sine of this side, and that's going to isolate phi. So sorry for just kind of scratching out steps, but sometimes that will improve if you're making errors. So we have phi is inverse sine er, that ratio, e divided by r, times the sine of the angle theta. Hell yeah. So now, for our equation, I can throw this in here, and I know what theta is. I just don't know what theta dot is. And actually, at this point, I don't even know... okay. But that was the whole thing, is like differentiation, you should never box yourself in. The only time I box myself in on this, and let me talk about this, is I divvied up y as I said, hey, I specifically said that this was like y1 and this was y2. and I took, I basically made an equation where I wasn't just deriving y1 dt, and then deriving y2 dt, and then adding those two derivatives together to make y. For whatever reason, these got like caught up into other equations, and I could never get them back. You know what I mean? Hell yeah, I know that and then so this is just going to be y1 dot, y2 dot, and this would be dy dt is just y dot. So doing the dots just really easy because you don't have to write, you know, the derivative of y dt. You know what I mean? It's a velocity. If y is a position in meters, then taking the derivative will give you velocity. So these are all velocities, and so yeah, the equation would be y dot is equal to y1 dot plus y2 dot. But the only issue is like they were just so cluttered up, I could never like get them separated again. All right, hell yeah. But so cool, we have another equation, and this equation, it doesn't have any velocities. I mean, yeah, so it's we have meters here divided by meters. Those cancel, so that is dimensionless. Sine theta is a percentage, so this is all dimensionless. It's just a ratio, and when we take the inverse sine of it, this gives us an angle. So that angle is in radians, and then there you go, and we have radians over there. And for all intensive purposes, radians are dimensionless until you start multiplying them by the radius. Then you get something useful like arc length. Okay, but what I guess I'm getting at is that we can just take the derivative of this with respect to time, and that's going to give us phi dot. Cool, and that's part of the equation right there that we don't have. You know what I mean? So taking derivatives is similar to just like doing 2D geometry and finding like the missing part that you're missing. Typically, you'll find it and get like a number, hopefully, but sometimes if you don't have numbers on things, the missing part might be, you know what I mean, maybe like this, just like this. Hey, I found the angle phi. There you go. It's just this equation. But I think we're used to it because it seems like it doesn't have any moving parts. The second we differentiate with respect to time, now we have velocities. And like, what does that mean? Well, it means that as this angle, well, it gives us an equation. If phi is related to theta, the derivative of phi with respect to t gives me the angular speed in theta, but it gives me that angular speed at any input of the angle. Remember how I said, like, hey, if we let's see, so like right here phi is nothing, but then like you know what I mean, hey, it's slowly getting bigger. Oh, now it's getting pretty big. And then, you know, like actually phi might be the biggest change right through here, because of this is tangent, and then once it's to here, actually there's a huge sweeping range where this angle phi doesn't change. So it's always good to also figure out, like, hey, we're wanting phi to change, or we're trying to notice how this angle changes, but we also might want to know how it's accelerating. You know what I mean? Is the change changing? You know what I mean? This angle's changing, but now it's not changing a whole lot, even through this tangential sweep from here to here. But from here, it's about the same angle to there. Whoa! It just, you know what I mean? So that 45 degrees, it went from here to there. Where this 45 degrees, it's already here. And I don't know. It really didn't do a whole lot. You know what I mean? So, and then you're going to get zero change right through here. So that's kind of the cool stuff that I can show. And that's always good because essentially we're going to get an equation for phi, and it's going to tell you how it's changing in relationship to this angle. We just kind of spelled it out. All right, booyah. So we're going to take the derivative of this, and we need a new sheet of paper, and this is where some of this stuff gets maddening. So I'm going to say that phi is inverse sine e divided by r sine theta, and we're done. And we're going to take the derivative with respect. So d dt on this side, I don't have a t in here, but I do have a theta. So I can go d theta dt. And then instead of writing d theta dt, I'm just going to write theta dot. This will be this is king when just like making less motions with your pen. And you can, I don't know, you can kind of just see that this is a variable unto itself. And don't we know what theta dot is? Hell yeah, we know that theta dot's 104. It's just a constant. It's actually just a number in this case. Where phi won't be a number. Phi will be a changing value given any input of theta. All right, hell yeah. But given the input of theta and the radians, that's it. You know what I mean? We can find the angular speed, because this is going to be theta dot. We can find the angular speed of that angle that we were doing at any input of theta, because this is just constant. So any angle theta, we'll know what the angular speed is. You know what I mean? And all right, so let's do it. Now this one is going to be a pain in the butt, because I don't know. It's probably the harder one. I'm going to make other videos on like, hey, I don't want to go to my book. How would I figure this out? Oh, hell yeah. No, I can. Like, let me do that, since I know what the hell I'm doing. So I'm just going to always draw like just a generic 30-degree angle, and we have phi. Now, sine says, hey, it's going to be this and then the hypotenuse, that. So it's going to be this divided by that. You know what I mean? Let's say I do this as a circle. It's going to be this rectangle divided by this circle. Okay, so, and that makes a ratio. Now, if I take the inverse sine of this ratio, what do I get? I get this angle. Cool. So, so the only thing that you have to do is like, hey, all you got to do is take this inside box and then just divide it by 1. And then what you just did is like, hey, I just found this side of the triangle, because it's a ratio between this side and the hypotenuse. You know what I mean? It doesn't matter what these numbers are. It doesn't have to be a unit triangle. This doesn't have to be 0.5, and this doesn't have to be 0.866. This could be double that, multiplied by 2. This could be multiplied by 2. You know what I mean? So, so just dividing by 1, it doesn't give you a unit triangle. In this case, it does, actually, because the hypotenuse is 1. I just want to point that out. But anyway, but when it comes to tangents or things, sometimes it doesn't give you a unit, but you can do that. You can be like, hell yeah, now I know something about this side. So let's draw that triangle again. And we know that, and then what are we trying to find? Because originally, this equation said phi was inverse sine of ER sine theta. There you go. So, so this is phi. So this is the angle phi, and we're saying that this side is E divided by R sine theta. Now, is that even true from our problem? Holy Toledo. Because if this is phi, we were saying that this was E divided by R sine. If this was E divided by R sine theta, the radius is 1. You know what I mean? So we are what I think what we're doing like is a unit triangle. It's kind of very fascinating. But let's go with it. Now we can find this other side, and we can say. Now I gotta see if like what are we actually doing here? We are. Yeah, honestly, I don't even know. But yeah, let's say I don't even know what we're doing. But you can always do, this is always a property of trigonometry that you can do. So we have the hypotenuse, we have a side. Let's find this other side. Using Pythagorean's theorem, this side squared plus this side squared is equal to this side squared. And we could find, you know what I mean, we could find the hypotenuse just by taking the square root of these two sides squared. Like, that's typical. I think everyone kind of knows that. Hypotenuse is those two things squared, but the square root of it. But you can also solve for b. So if we take a squared plus b squared is equal to c squared, and we want to solve for b, let's take c squared minus a squared. Okay, we're on the right track, and then take the square root. So hell yeah. And this is one that you should just know just off the top of your head. Hypotenuse is always the larger number. So I'm going to take that squared, and I got to subtract it by this squared. So we're going to have e squared, r squared, sine squared theta, and then we're going to take the square root of it. Okay, hell yeah. So now we're good to go. And all right, hell yeah. Sorry I went even down that rabbit hole because I don't know what to do with that. So we pop out our book. So if we want to take the derivative of inverse sine, I think I'm close, but not really, because inverse sine says this is a ratio. Cool, it's a ratio of a triangle. It's always good to be like, what is inverse sine? If you take the inverse sine of something, it has to be a ratio of this divided by the hypotenuse. I mean, that's what you're doing. You're trying to find the angle given the opposite, the ratio of the opposite over the adjacent. So cool. And then the ratio of this is going to give you that angle. So if I have a ratio, let's say I have a ratio of 1/2, that means that this opposite has a dimension of 1, and the hypotenuse has a dimension of 2. And sometimes you have to kind of fudge this to get the 90, and then there you go. So I have a 90-degree angle there, kinda, and then so this is 1, this is 2. There you go. So that's going to be what the angle of this is going to have. The sine of the angle is going to be 1/2, and the inverse sine of 1/2 is going to give me this triangle. Like with this angle. If I have this ratio, this triangle can only be one angle. All right. But anyway, so I don't think there's. Yeah. The only way to actually, man. Yep. I think to solve this, you have to bring the. If you wanted to solve this. Like a G, you would bring this over here to this side, and then derive it. You would say sine phi is equal to ER sine theta, and then take the derivative of both sides with respect to time, and then you would have to isolate phi again, and do it that way. But we're not going to do it that way because I'm not quite 100% on that. But at least I can look up this. So if we're going to take the derivative of inverse sine, the form is, so we're going to have dx inverse sine of u is going to be 1 divided by the square root of 1 minus u squared, and then du dx. Cool. And just as a caveat that you got to go from negative 90 to 90, which we are on this, so this is going to work great. And okay, and it's a u substitution. All that means is that I'm just gonna. It's kind of like ignoring the stuff on the inside. Kinda. But we still have to take the derivative of the stuff on the inside. But for the time being, we're just gonna say the derivative of inverse sine is 1 divided by the square root of 1 minus everything in here squared. So that's e squared, r squared, sine squared theta. Cool. So we did that part. Now we got to take the derivative of what's on the inside. E and r are constants, so we're going to go e divided by r. We're going to take the derivative of sine theta. That's going to be cosine theta. Now we're taking the chain rule, so we're taking this with respect to theta, but we still got to multiply it by theta dot. All right, hell yeah. So this is phi dot. And cool. And so we're done. And holy Toledo. So where did we leave off? Oh yeah, so yeah, we started just with a generic equation, like relating these two things. I didn't want to get this in terms of theta. In part 4, I do. I say, hey, this is going to be r squared minus e sine theta squared, and then square root that. And then I have both of these in terms of theta, and then I'm just done. But this is kind of the more complicated process. But hell yeah, I'm game for it. So yeah, let's go back to here, and where did we get? We got to here. We said that v of a was r negative 1 sine phi. So now we can throw in our equation for phi. That's going to be right here. So we're going to say sine of phi, and phi is inverse sine e to the r sine theta. Cool. Hell yeah. So that's phi. But see how we have sine of inverse sine of sine? You know what I mean? A lot of that, that's why I was trying to do this, because I think you can clean that up. But still, it still works. This is the ratio. If I'm taking the inverse sine, I must get an angle. If this is the angle, I take the sine of that angle, and then I get the ratio, or the percentage. Cool. And then that percentage times the radius. So all this is missing is some, this just gives me meters. So where are we at on the velocity? This velocity was r negative 1 sine phi, but now we have phi dot. And now phi dot is this thing. And I'm just going to write phi dot and then just point to that. I'm not going to rewrite that. And then we got plus e negative 1 sine theta. And now we got theta dot, which we know is just that 104. We're going to throw in 60 for this. E is 60 millimeters. R is 100 millimeters. And so we have everything. You know what I mean? 60 degrees here, 60 degrees here, 104 there, 100 millimeters here, 60 millimeters there. And then booyah. So now it's just plug and chug. So we did it. I might make a couple videos because, I wasn't even expecting to do it that way. But it worked out. And that was like just, hey, I'm going to set it up. I know that if these two values change, that's going to be the velocity. And adding the changes together, so getting this equation and taking the derivative with respect to time is that change in y. That change in y with respect to time is the velocity of that point A. And hell yeah. Booyah. So let's just plug this into our equation calculator and see if we can get the answer. But even right here, it's just like, look how messy this was. So I'm going to just make sure r is 100, alpha e is 60. What else? Theta is 60. And omega is that 104.7. So booyah. So we're going to start here. We got alpha r. See, this is why I bracketed my negatives. I just won't go wrong. You're not subtracting anything. You know what I mean? You're just you're multiplying by a negative. So hell yeah. So it's just a sign change. So we have sine, inverse sine. Whoa. Inverse sine, alpha e. Now you can just do this. Divide by alpha r, and the next term will go on top. You don't have to put any extra brackets in your calculator. It's not divide by r and sine. It's just e divided by r. The next thing is going to be on top, sine theta. So then I don't have to put a million parentheses. Okay, so that's going to be the er sine theta. And then bracket in, that's going to be the sine. Okay, we're done there. And now we got to do this. So even for this term, I'm going to say this is, I'm just going to put this all, this downstairs thing, I'm going to put it upstairs. I'm going to go 1 minus alpha e squared divided by alpha r squared, sine theta squared, end parentheses, but then I'm going to put it to the negative 0.5. So that puts the square root on it and then inverts it. You know what I mean? I have it upstairs in my calculator. The negative puts it downstairs. The 0.5 puts the square root on it. All right, booyah. All right, so now alpha e divided by alpha r. And then we have cosine alpha theta and then alpha omega. And hell yeah. Okay, so that's just that term. And then we got to add it to alpha e negative 1 sine alpha theta, and then omega. And hell yeah. So I've been getting pretty good at this. So definitely bracketing in the negatives. But differentiation, like I've spent 3 days, you know, doing this where I'm always going to make one sort of error. Usually I forget about this, but we already went over that. Check your units. We have meters here. This is dimensionless. You know, sine of an angle is just a percentage. And then this is going to be radians per second. So that's going to be 1 over second. Radians is dimensionless. So hell yeah, we got meters per second. So that checks out. Even here, ratio, angle in radians, dimensionless. Sine of an angle is a ratio, dimensionless. We have meters, and then this is radians per second. So that's going to give us velocity. All right, booyah. And we get the answer. VA is negative 3752 millimeters per second, or negative, I'm sorry, I'm just writing this horribly, 7352. So, or 7.35 meters per second. That's that velocity of that follower. Okay, hell yeah. And so this is the brutal beast, is like we just came up with an equation for, this was y dot, dy dt, also velocity of A. So if we wanted to find the acceleration of A, we would differentiate this with respect to time. And this is what you're going to run into, where if you don't find ways to kind of figure out how to simplify it from the start, these things are going to be real ugly, and you're going to have to go to online calculators. But even the differential calculator online is not going to take the differential with respect to time. It's not going to do the chain rule for you. It can, if you have a piece that's going to be, hey, the differential of this with respect to theta, it'll do that. And so you'll have to do like a bunch of those and do printouts to actually maybe get the right answer. But that's the only thing with that differential calculator online. It's not going to differentiate with respect to time when your function is a function of theta. And it's just not. And so it's not going to put these theta dots in all the right places. And so, yeah, I don't know. But maybe it's not that big of a deal, because maybe I'm just learning on the fly too. Because I think from here, it's just like there was no difference between differentiating this with respect to phi and then just slapping on whatever. Nah, because, yeah, sometimes, yeah, I don't know. You can't just throw a theta dot on the differential. I think if it's a product rule, sometimes some things will have a theta dot, and other times it'll have some other variable change. If R is changing, you're going to have an R dot, and you're not going to have a theta dot. So, yeah, that's the only bummer about differential calculators, is they can only do parts of some of these problems that are complicated. All right, booyah, that was brutal. But the only way I'm gonna get better is just by trying. So we're going over differential equations. I guess I'm just satisfied with getting right answers and not making any sign errors or just little calculator mistakes. But booyah, booyah. All right, thanks for joining me on this one, and that's the video.